In this video, we will discuss the London dispersion forces in more detail. The London dispersion forces, again, the temporary dipoles that result from the movement of electrons and distortions of the electron clouds that surround the atoms or molecules. And if this then results in an unequal distribution of electrons, then we can end up with a portion of the molecule that is temporarily a negative portion of the molecule, and then it would be a corresponding temporary positive portion of the molecule. And this would then influence the interactions with other types of molecules that can also have these temporary dipoles. In this slide, we can just try to describe how these temporary dipoles interact with one another. If we were to take two helium atoms that are relatively close proximity to one another, an individual helium atom would have two protons in the nucleus and two electrons that are forming the electron cloud. And usually the negatively charged electrons will be repelling one another and try to be as far away from one another as possible. This results in the two electrons being on opposite sides of the atom. But if the two helium atoms that have this situation come close to one another, they do not really have any way of balancing out any kind of charge, and this would be a net not attractive force or a non-attractive force between the two helium atoms. However, if at any moment in time one of these helium atoms has the two electrons in relatively close proximity to one another so that they end up on the same side of the atom, we would then have a temporary dipole, and that temporary dipole would result from the fact that we have the negative electrons on the left side of the molecule at this point in time, and the nucleus would be on the right side. Likewise, then the second helium atom will be influenced by this, and as a result, it would distort the electron cloud and then result in an attractive force between the two temporary dipoles that have been created, as you see down here to the right, and this would be similar to a molecule that has a dipole moment. Unfortunately, this is a very fleeting kind of interaction because the electrons oftentimes will then move back to their original positions, and then there is no net attractive force over the vast majority of time. The London dispersion forces are the weakest of all of the intermolecular forces because they have the least likely interactions of opposite charges over an extended period of time. And so it turns out that all molecules that have covalent bonds exhibit some sort of London dispersion force, in addition to possibly having other intermolecular forces. And so it turns out that if you have more and more atoms with more and more electrons, the probability that the London dispersion force is significant increases. And so the bigger the molecule, the more likely that you could have a distorted electron cloud, and therefore the strength of the London dispersion forces increases for big molecules compared to small molecules. So things like comparing pentane to isopentane to neopentane, the structures are such that if the molecule, these are all isomers of one another, and if the molecule is generally quite compact, as you see in the neopentane, then it's less likely to have a distortion of its electron cloud, and as a result of that, the intermolecular forces of neopentane would be weaker than that in something like pentane, which could have a slightly greater distortion of the overall electron cloud. A significantly stronger intermolecular force is known as hydrogen bonding. This is an intermolecular force that results when a molecule contains a hydrogen atom that is covalently bonded to one of three atoms. These atoms being very electronegative atoms, such as oxygen, nitrogen, or fluorine. And then the other requirement is that the oxygen, nitrogen, or fluorine also has to have a lone pair on that atom, so that the interaction between the hydrogen of one molecule with the lone pair of another molecule results in the formation of this hydrogen bond, as you see here. So it's possible then that have a whole variety of molecules in which you have these polar covalent bonds between hydrogen and fluorine, and then also exhibit these lone pairs. And these molecules tend to have relatively high boiling points and melting points as a result of that. The classic example of a molecule that exhibits hydrogen bonding is the water molecule. And so as a result, if you have this intermolecular force between a water molecule and the hydrogen that is covalently bonded to an oxygen, there is this intermolecular force represented by the dots that you see here between a lone pair and the hydrogen of another molecule. And these are relatively strong intermolecular forces, and as a result, these forces of attraction are relatively difficult to break. And this results in the shape of the molecules in the solid state, in the ice structure, and then also has a significant effect on the melting and boiling points for water in comparison to other molecules that don't have hydrogen bond. Finally, we have the ion dipole forces, which are the interactions of polar covalently bonded molecules that have dipole moments with ionic compounds. And a classic example of this is the fact that an ionic compound such as sodium chloride dissolves in water so that the positive and negative ends of the water molecule will interact with the oppositely charged ions and facilitating the formation of a solution. So oftentimes when sodium chloride is dissolved in water, the positive hydrogen end of the water molecules will interact with the chloride ions, whereas for the sodium ion, which is positively charged, that will interact with the negatively charged oxygens, or the partial negative charges of the oxygens of the water molecules, which surround this ion. And of course, this then results in a whole network of hydrogen bonding interactions with other water molecules and the formation of the solution. This also facilitates the movement of these ions throughout the solution and readily explains why the sodium chloride aqueous solution is an electrolyte solution. Can quantify the energy associated with breaking these intermolecular forces in comparison to the intramolecular bonds that we have been describing for molecules and ionic bonds for ionic compounds. You can see that the London dispersion forces are quite weak, and they range from hundreds of a kilojoule per mole to tens of kilojoules per mole, depending upon the nature of the molecule. But they tend to be, overall, on average, weaker than the dipole-dipole interactions for molecules that have dipole moments, whereas those bonds tend to be weaker than the hydrogen bonding interactions for molecules that can form hydrogen bonds, and of course those are weaker than the so-called ion dipole interactions. All of these intermolecular forces are significantly weaker than the intramolecular bonds, which generally for ionic compounds are 600 to thousands of kilojoules per mole. Likewise, for the covalent and polar covalent bonds, these tend to be in the hundreds of kilojoules per mole, and are significantly strong bonds.